So let us begin at the zeroth order. Now this problem, of course, is just that of flow between flat plates. Now the governing equations, as I said, stay the same. It's only the boundary conditions now which reduce to u0 and v0 equal to 0 at y equal to half for the top wall and the corresponding symmetry conditions. So although the equations are the same, what has changed is that the boundaries have now come to conform with the Cartesian coordinate system, which is what immediately allows us to recognize from the fact that v is equal to 0 at y equal to 0 and at y equal to half, that we can simply say v is equal to 0 throughout the domain, which satisfies dv by dy equal to 0 and both boundary conditions, which is not possible when we had the wavy wall. And from this we of course get that u is fully developed, which then from the momentum equation will simply tell us that d square u0 by dy squared equals -1, after recognizing that the of course the pressure perturbations don't exist at this order. Even if we had included functions basically g0 and f0, we would find them to be 0. And so the solution to this problem, of course, along with the boundary conditions, as follows. Is basically given by simple Poisson flow between flat plates, which we have derived before. So I leave you to work out the details. It's a very simple solution, and v0 of course is 0. Okay, next let's go to order of epsilon. So now we cannot say v is equal to 0 because well, in the full problem is because the boundaries do not conform with the coordinate system. In the perturb problem, the boundaries are in conformation with the Cartesian coordinate system, y equal to 0 and y equal to half. But now the boundary condition on v is not v equal to 0, but rather this perturbed form where v is, basically a Taylor series expansion. So v is no longer 0 at y equal to half. And we can then substitute u and v into their corresponding boundary conditions at the wall, at the fictitious wall, or the wall of the base domain y equal to half, and obtain the corresponding non-homogeneous boundary conditions, which is what will actually give us the two-dimensional velocity field. So let us first write out the domain equations. Right, so I have the equation of continuity. I then have the equation for u. Right, there is no contribution from 1 because I'm looking only at the terms of order epsilon after substituting in the perturbation expansions. And so what I will get is simply g1, which is the order epsilon correction. So you'll see that all the terms in the domain equations are of the same order. This is because there was no epsilon in the domain equations. Unlike the previous perturbation problems where when you have epsilon in the governing equations, you will get a term from the previous order appearing as an inhomogeneity in the term of the current order. Here all the domain equations are homogeneous in the variables at the same order. It is the boundary conditions which introduce terms from the previous order and which act as inhomogeneities in the equations. So g1, remember, is a function of x comma y. It is not a constant. And then we'll also have the equation for v1. Alright, so these are equations 7 ABC correspondingly. Alright, and the most important thing, of course, which will instruct us on how to proceed with the solution is the boundary conditions. And that's what we'll get now by going up to this equation. Let's look at the boundary condition for u at y equal to half first. So when we substitute the expansion, we'll get u0 plus epsilon u1. We'll take, of course, the u1 term at order epsilon. Similarly, from here, we'll get dou u0 by dou y multiplied by epsilon, which will survive at order epsilon. The dou u1 by dou y is an epsilon square term, so we don't take it at this order. And well, this term has no contribution at all, because even if I take u0, it's already epsilon square. So the only term I have is u1 coming from here, and then the derivative of u0 with respect to y times sine 2 pi x by 2, which is equal to 0. So if I take that to the other side, I can write out the final boundary condition for at y equal to half as u1 equals minus sine 2 pi x by 2 times dou u0 by dou y. Of course, we know dou u0 by dou y from here. I just take its derivative and I evaluate it, of course, at y equals half. Indeed, by inspection, you'll see dou u0 by dou y just gives us 1 by 2 into minus 2y, which is just minus y, so it's just minus half. So this entire thing is sine 2 pi x by 4 actually, but let's leave it in this form for the moment. So you can see how the zeroth order problem appears as an inhomogeneity via the boundary condition for the problem at order epsilon. Similarly, I'll have an equation for v1, of course, because it has the same boundary condition. Right, but now dou v0 by dou y is 0 because v0 is 0, so we get v1 is equal to 0, again at y equal to half. And then of course you have both dou u1 by dou y equal to v1 equal to 0 at y equal to 0, because that symmetry boundary condition is unperturbed, which is one benefit of replacing the no-slip boundary condition at the bottom wall by this symmetry condition. But a purely calculational algebraic benefit for ease of calculation. It doesn't really change anything in the problem, as I had mentioned earlier. Alright, so now we can look at how we solve this problem. So once again we see that we have well, yes, we have the boundary conditions on u, on v, as well as the equation of continuity. So the strategy we're going to adopt is the following. We'll first solve this equation for u1. We will then go ahead and solve the corresponding, we'll get, if we can solve for u1 from this first equation, we can then solve for v1 from the equation of continuity, and applying the boundary condition should allow us to determine the field for u1 and then thereby for v1 spontaneously together. And so this is why, so let's follow this procedure. But the first thing now is to figure out how to obtain a solution to this PDE. One common way is to see if we can obtain a solution in a separable form, whereas by that I mean we can write the solution for u1 as a product of a function of x and a function of y. And such a separable form is immediately suggested by the boundary condition. So since this equation is linear, we can expect and anticipate that the x dependence will be completely governed by the non-homogeneous term in the boundary condition. Right? So based on the boundary condition for both u1 and v1, we can assume that we can seek a solution of the form u1 is equal to phi1 of y, which contains the y dependence, times sine 2 pi x. And similarly, v1 is psi 1 of y times sine 2 pi x. If v1 and psi 1 are purely functions of y. Correspondingly, we need to express the pressure gradient in a form, and we use the same sign dependence because well, you can see already that if I take the derivative of the solution with respect to x, I'm taking it twice. So as sin x becomes cos x becomes sin x again. So if we take the dependence of g to be sin x, I can factor out the sin 2 pi x throughout and get an equation ODE only for phi1. So let's say that g1 also has a separable form, right, that goes as let's call it c1 times sine 2 pi x. Okay, so we can now proceed. Oh yes, an important point to mention is that we are here assuming that g1 is only dependent on x and that c1 is a constant. So what we are saying is that we are going to seek a solution where the perturbed pressure gradient in x is independent of y. So the perturbed pressure itself depends on y, but the derivative of that pressure with x is y independent. So we will assume this as a solution, as a relatively simple initial guess, and we will see if it satisfies the equations, then we'll know that our guess is right. Okay, so let's proceed with this, noting that c1 is a constant. Oh, also, v1 has the same periodicity, but it's not sinusoidal. That's my mistake. It's actually cosine. Right, that follows from the continuity equation that if u1 goes sinusoidally as sine, it's a derivative of u1 with respect to x that sets the dependence of v on x, so it should be cosine. But the best thing to do maybe is not to suggest anything for v1 and let it emerge naturally from the continuity equation. Right, so since we had first decided to solve for u1, we just make assumptions on u1 and g1, solve it, and then we come to the continuity equation and we can directly determine v1 as required. So let's not yet specify anything for v1. Alright, so let's start from here. And just substitute this ansatz into the governing equations at the boundary, specifically into equation 7a and the corresponding boundary conditions. Let me just call them 7d and 7e. So what we'll obtain, the second, we'll simply get rho square phi1 by rho y square, sine 2 pi x comes out, plus we'll have lambda squared, of course multiplying, now we take two derivatives with respect to x. This sine 2 pi x will give me a 2 pi times 2 pi the whole squared, negative, so when sine goes to cosine I'll get a 2 pi, when cosine goes back to sine I'll get a negative times 2 pi times sine 2 pi x again, and the phi1 will just pop out of that derivative, and the sine x will cancel throughout and I'll be left with a constant c1. Okay, so this is a simple ODE and we can recognize that it will have an analytical solution. So if I ignore c1 for the moment, which can be dealt with an inhomogeneous solution, I have an homogeneous equation which I have rho square phi1 by rho y square is equal to 2 pi lambda the whole square phi1. This has a solution of sin h as one homogeneous solution, cos h as the other, and then I have a particular solution which I can assume to be independent of y and find to be just c1 divided by 2 pi lambda the whole squared with a negative sign, of course. So the total solution that I can write down involves the particular solution that I would obtain as follows, plus the homogeneous solution involving the cos h term, and I should also have the second homogeneous solution as follows. Right, now we can apply boundary conditions. So if I apply the symmetry condition dou u1 by dou y, which is basically dou phi 1 by dou y. So if I put dou phi 1 by dou y at y equals to 0 equals 0, we'll see that this must imply, now dou phi 1 by dou y, this makes it sin h of y going to 0 is just 0. This becomes cos h of y, which is 1, which implies that well, basically this would imply that b must be equal to 0. The homogeneous term, of course, is cancelled after taking the derivative. So this just tells me b equal to 0, and I don't have this term. So then I just have the unknown constant a, as well as the yet to be determined constant c1 coming from the pressure gradient. So for a, I can now use my other boundary condition at the wall, right, of the base domain. So at y equal to half, of course, I have the next boundary condition, which is just the condition specified here. So if I substitute u1, and this is by construction, of course, this will be phi 1 sine 2 pi x. The sine 2 pi x cancels from both sides, so I get phi 1 is equal to minus 1 by 2 dou u naught by dou y and as I said from here, dou u naught by dou y is simply so I'll get half times minus 2y evaluated at half is that half times minus 1, so I get minus half, and minus half times minus half will be plus 1/4. So substituting for phi 1, right, I have minus c1 by 2 pi lambda the whole squared plus a cos h of pi lambda after substituting y is equal to half is equal to 1 by 4. Right, so therefore I can now solve for a. The whole, of course, divided by cos h of pi lambda. Right, so all I now have, so I determined a in terms of c1. So I only have the as yet undetermined constant c1 left in my calculation for u. So at this term, at this point, I cannot get any more information out of the equation for u and its boundary conditions. So I then turn to solving the equation for v. So I could obtain the equation for v1 by solving this equation by integrating dou u1 by dou x with respect to y, and then applying both boundary conditions for v on this problem. However, at this stage, since our main goal is actually to determine the flow rate, and that only involves the calculation of u, we can now take a shortcut and just directly determine u1 entirely or in other words determine C1 by using the condition we derived earlier that ddx of q must be equal to 0. Now this condition, when applied on our expansion for q in a Taylor series, essentially means that the derivative with respect to x of the integral of each component of the solution of u at each order must be 0, right? So I can now determine C1 without calculating v by using the condition on the flow rate, which, as we had said, was just another re-expression of the boundary conditions on v as well as that on u. But at this point it's convenient because it allows us to complete the calculation for u without ever solving for v, which is great for our at least one of our goals here, which is to calculate only the change in flow rate. So the fact that ddx of q equals 0 must imply, of course this is automatically satisfied at the 0th order because q is independent of x, and at first order it basically means that of the integral from 0 to half with respect to dy of the function phi1 of y, right, times sine 2 pi x, and this must be equal to 0. So clearly the derivative of sine 2 pi x will leave me with cos 2 pi x, and so for it to be 0 it must mean that this coefficient of the function of x is 0. So this condition basically boils down to the fact that the integral from 0 to half of phi dy must be equal to 0. So I can now, so this gives me another condition directly to calculate C1 in terms of A. So I come back to my solution here for phi1, substitute it in, take the integral with respect to y, and see what the equation gives me. So the first term of phi is of course just this constant. Integrating with respect to y will be this constant times y. Evaluating the limits, of course, at 0 gives me 0, and at half will just give me half. So I'll get minus c1 by 2 divided by 2 pi lambda the whole square, right, coming from the first term, plus a, which I now know in this form, right, plus a times cos h 2 pi lambda y. This becomes this becomes sin h 2 pi lambda y, and now y is of course half, and the limit for 0 would give me 0, but then I also have 2 pi lambda here sitting in the denominator, must be equal to 0. So the half cancels out with the 2. I can remove a 2 pi lambda factor entirely. This sin h by cos h just becomes tan h, right? And so I therefore have tan h into 1 by 4 plus tan h times this constant is equal to minus half of the same constant, I mean without the 2 pi lambda. And so if you rearrange this, you can see that you can expand it out, collect terms of C1 on one side, and I leave you to show that the final expression you get looks like this. And there is a square here, yes. So this is my expression for C1. So now having determined C1 as well as A in terms of C1, I have the full solution. I have Phi1 and therefore I have the full solution for U1. So U1 has now been completely determined. But so now we could say, can I go and get a correction to the flow rate? But as we already expect, this should not give us any contribution. If we want to go and substitute it back in, we can, but what we would find is exactly what we found. In fact, that was what we used in this condition, right? So if I calculate the condition here, right, we obtained that integral of phi with respect to y is 0. So if I calculate the correction to the flow rate, which is basically right, so q, remember, is q naught, so let's say q by 2 is q naught by 2, which is the integral of u naught, which is the base state flow rate, right, plus at epsilon it's the integral from 0 to half of u1, which is basically phi1 dy times sine 2 pi x. But as my condition implies earlier, this is exactly 0, and this makes sense because u1 has no component that is independent of x, so it cannot make a contribution to the flow rate, otherwise the flow rate would become x dependent. This is 0, and therefore I have no correction to the flow rate at order epsilon. But of course there are order epsilon square terms which we are yet to determine, and therefore to calculate the change in the flow rate, we now move to order epsilon squared. Before that, we should make some comments about the rest of the solution. So I fully determined u1 right now. Based on that, I can just come in here, substitute u1 here, which is completely known, integrate 1 with respect to y and apply one of the boundary conditions, and that will give me v1 completely, right? I still have another condition on v1. If you will see that other condition, whichever I have not used when I calculated v1 here, will get automatically satisfied by the solution. This is not surprising because by using the condition that the flow rate is independent of x, I basically use some form of one of these conditions. So whatever leftover condition is there will be automatically satisfied. So I can fully determine v1 from here, and I can then go back to this equation and directly calculate g2, because I now know v1 entirely. So I can then calculate g2 from here by doing that's it, by just evaluating these terms. Now it may seem surprising that how g2 was completely determinable, even though it seems like an extra unknown, but really it's not, because you remember g2 and g1 are simply different gradients of the same quantity, which is pressure. So they are both actually intimately related and therefore not independent unknowns. So it should not be surprising that once I calculate u and v using the corresponding boundary conditions and I use a continuity equation to determine g1, g2 gets automatically determined. So you can go ahead and calculate the entire solution to first order, and you can even plot the streamlines, and what you will see unsurprisingly is what we had anticipated if you had zoomed in this area near the wall, that the streamlines sort of will follow the wall, right? The perturbed velocity u1 we'd expect for positive epsilon to be greater than 0 as it accelerates into the wall. Sorry, I should say that as the fluid is moving into the wall, I should find that u1 is greater than 0, but v1 will be less than 0. Similarly, when the fluid goes into the diverging sections, I'd expect the fluid to decelerate relative to the base state solution, so u1 should be negative, whereas v1 will be positive as the fluid moves upward. This out of phase behavior, of course, is apparent from the continuity equation, because if u1 goes as sine 2 pi x, v1 will go as cosine 2 pi x, as implied by the equation of continuity. So the signs of v1 and u1 and v1 will be opposite, and that makes sense with this type of diverging flow. And the pressure gradients also would be, the perturbed pressure gradients will also be same. So as the fluid converges, you will see that the pressure gradient in the x direction will be negative, allowing the fluid to accelerate, whereas the pressure gradient will be positive, meaning the fluid will go into regions of higher pressure, causing it to essentially decelerate. However, you should make sure that this negative and positive pressure gradients are only the perturbed pressure for small epsilon. The overall pressure, of course, is these pressure gradients plus g, which is significantly order 1 constant. And therefore, the overall pressure, if you measure with a manometer, is always falling down the channel. It never increases along the flow, which makes sense because for a creeping flow, you cannot have flow into an adverse pressure gradient. It has to constantly be decreasing because it's the only source of momentum. You have no inertia to overcome adverse pressure gradients as you do in non-creeping flow cases. Okay, so with those few comments aside, let's now pursue our main goal to calculate the change in the flow rate by going to the calculation at order epsilon square.